Hello everyone and welcome back to this video. So in this video we're going to um, dive deep and start learning about the DeepSeek model that has been released pretty recently, and it has taken the world of LLMs and large language models by storm. And for for a few months, let's say, I have been away from the world of LLMs for some reasons, but now I have come back and I've seen this model that has like literally taken the world by storm, and like many people are making a lot of content and sharing their appreciation, and many are impressed by this model. So I've decided to in this video we are going to uh, together start studying the research thesis of this model, and what they use, and their approach uh, with which this DeepSeek model really works, right? We'll also go through the math behind the DeepSeek model. So we're going to use some articles to study about this model. So the links of the articles will be shared in the video's description. So please, check the articles all out also, right? So first of all, we have this paper that they have released on 22 January in 2025. So yeah, I mean, uh like, to be honest, like, I have no idea on this topic. So if you have come here to learn about DeepSeek, then this video might probably not be the best for you. I'm just using this video as a way to document my own learning journey. So anyway, so let's get started if you are still watching. So DeepSeek Carbon incentivizing reasoning capabilities in LLM via reinforcement learning. Okay, so we have abstract. We introduce our first generation using models, DeepSeek R1 0 and DeepSeek R1 R1 DeepSeek R1, model trained via large scale reinforcement learning without supervised fine tuning as a preliminary step, demonstrates remarkable reasoning capabilities. Though through RL, DeepSeek R1 0 naturally emerges with numerous powerful and intriguing reasoning behaviors. Okay, so from the abstract, we can see that DeepSeek R1 has a performance comparable to OpenAI O1 on reasoning tasks, and also that it doesn't use supervised fine tuning as a preliminary step. So until now, we have in all of the LLMs that we use, right, in large language models. So we have the first pre-training step, pre-training phase, where we train the model on generalized data that we find on the internet. There are many data sets, many famous data sets, right? So we'll train the models on this like we will pre-train these models on this very large generalized data sets, and then we will fine-tune these models on specific uh, very refined observations, or very refined uh, query answer pairs, right? And also we can have specific task depend like data sets that are for specific tasks, right? If you want to train a model for a specific task, we have data sets for that too. So that is called the supervised fine tuning phase. So this DeepSeek model seems to uh, skip, right? Seems to skip this step of supervised fine tuning, which is okay. Let's see what we have. So these are some data sets, I think. Yeah, my Math 500 is a data set. We have SWE software engineering bench verified. So that's I think it tests the software engineering skills of a model, right? It's a something related to coding, and we have code forces too, right? That is related to yeah. I mean, it does seem to perform very well in computational related and mathematical related tasks, and also tasks that are tasks that need reasoning skills. So this model seems to perform good at that, right? So let's dive right into the paper. We'll go through a paper, right? So we'll skip through the steps. We'll skip through. We'll just go through this paper at a very high level. I mean, not very high level. We'll try to, yeah. Okay. Mm, right. In this paper, we take the first step towards improving language modeling reasoning capabilities using pure reinforcement learning. Our goal is to explore the potential of LLMs to develop reasoning capabilities without any supervised data, focusing on the self-evolution through a pure RL process. Okay, they seem to employ a pure RL process, which is okay, very interesting. Like generally in RLHF, while we are training RLHF, we will train a reward model that that is trained on human preference data. So we have many humans rank the outputs of an AI model for one question. So for one question, we are given different outputs, possible outputs, and humans are give made to rank these outputs based on some predefined metrics. And after that, we'll be training a neural network generally in reinforcement learning based feedback mechanism like RLHF we call that. So we'll train a neural network separately. I don't think we'll be doing that here. So in a pure RL process, maybe they imply uh, that they'll not be using any neural network. That they'll not be training any neural network separately. Okay, interesting. Specifically, we use DeepSeek V3 base as the base model and employ GRPO. Okay, so let's see what GRPO means. Okay, I think this is yeah yeah. This GRPO. We have an article on that. We'll go through that just a minute, right? Okay. Numerous powerful and interesting behaviors. After thousands of parallel steps, DeepSeek R1 Zero exhibits super performance on reasoning benchmarks. Okay. We have AME, right? What is AME data set? Let's go through that. Again, I want to warn the viewers, if you are watching, that this video is not going to be me teaching you about DeepSeek because I have no idea what DeepSeek is. I'm just making this video as a form of to document, right? Uh, to basically like I don't know why I'm doing this, but it's certainly not for the purpose of teaching, right? I can say that. I mean, I'm just hang on. So what is AIM dataset? For the treasure love Trove challenges for the American International Mathematics Examination. Appreciate complex. Okay, okay. So like okay, maybe mathematical puzzles, right? Okay, okay. So related to mathematics. Okay, got it. Then what other models do you have? Like, what other data sets do you have? Okay. After $1,000, okay, increase from 50.6% to 71% with the majority voting. The score further improves to 86.7%, matching the performance of OpenAI O1. Very nice, right? So, DeepSeek R1 Zero encounters challenges such as poor readability and language mixing. Interesting. To address these issues and further enhance reasoning performance, we introduced DeepSeek R1, which incorporates a small amount of cold start data and a multi-stage training pipeline. Specifically, we begin by collecting thousands of cold start data to fine-tune the DeepSeek V3 base model. Following this, we perform reasoning-oriented RL like DeepSeek R10. Upon nearly convergence in the RL process, we create new SFT data through rejection sampling on the RL checkpoint, combined with supervised data from deep. After fine-tuning with new data, the checkpoint undergoes an additional RL process, taking into so they have like divided the training process into different phases, I think. So it seems that in their base model, which is R10, there were certain challenges such as poor readability and language mixing, right? Uh, right. Okay. So these are the contributions they have. Let's just go through the contributions, and after that, um s- we'll go through the approach, which will be the main point of this video, right? Which will main studying of these things. So first of all, let's go through the contributions. I think they have developed or are these or maybe this could be the preliminaries on which they have based their approach. Let's see what these are like. Are these the thesis that they have come up with? Okay, let's see. Okay, contributions. Post training, large scale reinforcement learning on the base model. We directly apply RL to the base model without relying on supervised fine tuning as a preliminary step, right? This approach allows the model to explore chain of thought for solving complex problems, resulting in the development of DeepSeek R10. DeepSeek R10 demonstrates capabilities such as self verification, reflection, and generating long COTs, making a significant milestone for the research community. Notably, it is the first open research to validate the reasoning capabilities of LMs can be incentivized purely through RL without the need for SFT. This big breakthrough paves the way for future advancements in this area. Okay, we introduce our pipeline to learn deep sea carbon. Thus, the pipeline incorporates two stages aimed at discovering improved reasoning patterns and aligning with human preferences, as well as two SFT stages that serve as a seed for the model's reasoning and non-reasoning capabilities. We believe the pipeline will benefit the industry by creating better models. Okay, they have claimed that pure RL is the way to go if you want to increase reasoning among the model. So what they have found that Deep Sea Carbon Zero demonstrated capabilities such as self-verification and reflection. Okay, and also it is able to generate like long chain of thoughts, like, right. So long. So chain of thought is like you are you ask the model or make the model not only give you the answer but also the reasoning and the steps that it took, and yeah, the steps that it took uh, to come to the answer, right, from the question. That is chain of thought. Um, right, got it, right. I mean, there's still a lot we have. Problem is, we will catch that in the article that we are going to read next. Okay, we'll just skip to the paper now. For now, distillation. Smaller models can be powerful too. We demonstrate that the reasoning patterns of larger model can be distilled into smaller models, resulting in better performance compared to the reasoning patterns discovered through RL on small models. The open source DeepSeek Carbon as well as its API will benefit the research community to distill better small models in the future. Using the reasoning data generated by DeepSeek R1, we fine-tuned several dense models that are widely used in the research community. The evaluation results demonstrate that the distilled smaller dense models perform exceptionally well on benchmarks. Right. So for the one thing for which I think that the one thing for which DeepSeek has got its popularity is because of its computational efficiency. Right. The amount of like it's very fast. Like if you are actually using it, right, post training. If you're using it post training, it is actually very fast, and I think that could be attributed to this process of distillation. So we have this technique called deep learning. In deep learning, we have this technique called distillation, where we take a very large model. Right, this model learns so many patterns, and I think the idea behind distillation is that uh, so this is called the teacher model. The large model will be called the teacher model, and this large model will be given some output inputs, and it will generate some outputs, and on the input and output pairs, I think the smaller models are trained. I think that is the idea. Okay, we'll just confirm. uh, let's see let's see how does distillation work. That's not the distillation that we are looking for. Deep learning. Mhm. Right. That's not. Wait, we'll just go through this article. Let's see what distillation is. That requires to transfer. Okay. Okay. Advanced fathom and universal approximators giving enough training data and large enough hidden layer. Okay. Is identified when it learns parameters. The variable weights are applied to the different medical. Instant hint and okay. Through this alternate understand knowledge, knowledge research methods aim to train student models to mimic not just the teacher's model's final output for a given output, but also reasoning steps. Okay, got it. Mm. Model parameter minimize the slope or the gain of the vector through an optimized model. The model's output come closer to these corrected outputs, while the model's reasoning steps are important. In that, they influence its output. They're not okay. Conversely, also trains a student model to remove the teacher's modeling reason process through the addition of a specialized type of loss function, distillation loss, that uses discrete reasoning steps as soft targets. Okay, so we have in distillation, right? So yeah, I mean, I was right. Uh, so we have the teacher model, right, and which is the larger model, right? So we'll have this teacher model, and we'll compress this model. So this teacher model, so the knowledge of this teacher model will be distilled to a smaller model, and the smaller model, the student model, is asked. So it will be made to mimic the steps, the reasoning step that the teacher model took to solve the problem, and not only not only predicting the answer, but also it has to come up with the same steps, right? So it has to uh, come up with the same reasons. It has to think like the teacher, right? So that is distillation. Got it. Then uh, evaluations using tasks. Okay, so we have some results. It attains a score of 97.3%, performing on par with OpenAI O1, outperforming other models, right? It also uh, shows great expertise in coding competitions, right? Uh, it also outperformed many humans in coding competitions. Very nice. And we have also okay, we have these data sets MMLU. I think MMLU is let's see what MMLU is, right? Uh, yeah, knowledge acquired. So I think it's all objective questions. Yeah, it's objective questions, right? We have this data, this data set. I think it contains of many knowledge, like knowledge related in terms of like it's objective questions, right? Not subjective reasoning things. So yeah, it also has a lot of knowledge, right? Knows a lot of stuff. It can remember stuff, and hallucination, right? It's converse. It's like yeah, it doesn't hallucinate that much, I guess. Right. Yeah, now let's get to the fun part and most important part, interesting part, the approach. Right, I'm eager, and I hope you are too. We'll go through the approach uh, that the DeepSeek employs. Right, so we'll go through that. Right, previous work was has heavily relied on large amounts of supervised data to enhance model performance. In this study, we demonstrate that reasoning capabilities can be significantly improved through large scale reinforcement learning, even without using supervised fine tuning as a cold start. Furthermore, performance can be further enhanced with the inclusion of small amount of cold start data. In the following sections, we present DeepSeek RL0, which applies RL directly to the base model without any SFT data, and DeepSeek R1, which applies RL starting from a checkpoint, fine tuned with thousands of long chain of thought extra examples. 3. Distill the reasoning capability from DeepSeek R1 to small dense models. Right. Okay. So first of all, we'll be learning about DeepSeek R1 zero, uh, where we don't have any SFT, I guess. So they are calling something called cold start. Okay, we'll get to the part. We'll get to DeepSeek R1 zero. Let's see what it how it functions. Okay, right. I'll just pull it a little closer. Right. So yeah, reinforcement learning has demonstrated significant effectiveness in reasoning tasks as evidenced by our previous works. However, these works heavily depended on supervised data, which are intensive to gather. In this section, we explore the potential of LLMs to develop reasoning capabilities without any supervised data, focusing on their self-evolution through a pure reinforcement learning process. We start with a brief overview of our RL algorithm, followed by the presentation of some exciting results, and hope this provides the community with valuable insights. Right, got it. Right. So until now, like how LLMs function, right? We have a lot of, so we have LLMs and they're trained on like a lot of data, right? Uh, they are pre-trained on a lot of data, and uh, reinforcement learning, on the other hand, it doesn't need data to learn from. Like it doesn't learn from data. It learns through experience, right? So there will be a, let's say, artificial environment, and the model will be uh, making moves, right? In different contexts, like making moves means different things in different contexts, and each move of the model will be rated by a will be rewarded, right? We will have an algorithm or a model, right? In some cases, to reward the actions of the model that we want to train using our reinforcement learning, and the reinforcement learning model will be trying to maximize this reward, and in this process learns how to act better in that given environment, right? So that is how reinforcement works. Okay, let's get to the algorithm and let's see how this works, right? So group relative policy optimization. I have no idea what this means. Let's get to this. In order to save the training cost of RL, we adopt group relative policy optimization. Sorry, which forgoes the critic model that is typically the same size as the policy model, and estimates the baseline from group scores instead. Specifically for each question Q, GRPO samples a group of outputs O1, O2 to OG from the old policy, pi theta old, and then optimizes the policy model pi theta by maximizing the following objective, right? Okay, so in order to save training cost of RL, we adopt group policy optimization, group relative policy optimization. Got it? Uh, which foregoes the critic model that is typically the same as the policy model and estimates the baseline from group scores instead. Okay, I mean, we'll go through the math and also the article to understand this better. Okay, specific for each question Q, we have multiple samples. So we sample different outputs. O1 to OG, got it. From the old policy, pi theta old. Okay, so this is how we optimize. So we basically start off with a policy, uh, which again, like in the first step could be randomly initiated, and then we optimize this policy, uh, and like, and then we will uh, optimize the policy by maximizing this objective. So in supervised learning, we have something called loss function, which we'll try to reduce, which will try to find the optimal solution. So here we have here in reinforcement learning we have reward, which will try to maximize. So let's see what is the optimizing objective. So it is this, I think, from like all that. I think yeah. Uh, I mean, like, I have no idea about this notation, but let's try to come up with something. Uh, I have. I mean, okay, let's use DeepSeek to understand DeepSeek, right? Or maybe this is better to start off with. Okay, so this is the optimization function. Okay, yeah, in the paper, like the notation was, yeah, shit. All right, so right, let's go. Let's get through this paper first, and yeah. Yeah, I think everything we had a good introduction. So we'll pause this paper here and go through this article and come back to this paper to see, like, yeah, to understand better, right? So again, the credits to this to Sahin Ahmed, uh, I've got this article from Medium, so I'll post a link of this article too in the description. Check that out if you're interested. So this blog dives, okay, into math behind GRPO, the core reinforcement learning, the RL algorithm that drives DeepSeek's exceptional reasoning capabilities. We'll break down how GRPO works, its key components, and why it's a game changer for training advanced large language models. So, what is GRPO? Group Relative Policy Optimization is a reinforcement learning algorithm specifically designed to enhance reasoning capabilities in LLMs. Unlike traditional methods, which rely heavily on external evaluators, critics to guide learning, GRPO optimizes the model by evaluating groups of responses related to one another. Got it. So in traditional RL methods, we have external evaluators, external critics, either a model that will be trained on human rewards, majorly that. However, here in GRPO, we have, I mean, we seem to like evaluate responses relative to one another. I have no idea. Let's keep moving. This approach enables more efficient training, making GRPO ideal for reasoning tasks that require complex problem solving and long chains of thought. Again, it's more efficient because we'll not be having to train any external evaluator. Got it? So why GRPO or traditional RL methods like proximal policy optimization face significant challenges when applied to reasoning tasks in LLMs? Okay, so these are the problems with PPO, proximal policy optimization. Okay, dependency on a critic model. PPO requires a separate critic model to estimate the value of each response, which doubles memory and combination requirements. Right? Exactly. We need to train another model on human preferences, or the we have to train another model to reward the actions or the outputs of the LLM, right? Which is again computationally and in terms of memory, not efficient, very inefficient, right? So training the critic is complex and prone to errors, especially tasks with subjective or nuanced evaluation, right? So we like, yeah, I mean there can be subjective, like not all tasks can be uh or not all questions can be objectively answered with an yes or no, right? There'll be many nuances, and for that it's just too complex to train a critic, right? Got it. And we have high computational costs, like same thing. uh they like they depend like significant computational resources, right, to evaluate. uh and yeah, scaling also, right? We can scale it for large scale applications, right, with the complex chain of thoughts, right? Absolutely, what evaluation struggle with diverse tasks, making hard to generalize across training domains. Okay, now how GRPO addresses these challenges? So we have a critique free optimization. GRPO removes the need for critic model by comparing responses within a group, significantly reducing computational overhead. Got it? Relative evaluation. Instead of relying on an external evaluator, GRPO uses group dynamics to assess how well a response performs relative to others in the same batch. Got it, right? So we'll be comparing responses in a group relative to one another. The metric, I mean, will come to the metric in just a minute. Right, so we have efficient training by focus on group-based advantages. GRPO simplifies the reward estimation process, making it faster and more scalable for large models. Okay, so the main thing in GRPO seems to be simplifying the reward estimation process. So rather than having to train a specific another model, complex critic model, to rank the rewards, right, or reward the models outputs, we'll be simplifying the reward estimation process with something called, I mean, yeah, we don't have an idea of how they work, what all they do. We'll get to that in just a minute. So yeah, we'll be simplifying the reward estimation process. Got it. Key idea. At the heart of GRPO is a concept of relative evaluation. For each input query, the model generates a group of potential responses. Got it. These responses are scored based on how they are compared to others in the group, rather than being evaluated in isolation. Right. So advantage of a response reflects how much or better, how much better or worse it is relative to the group's average performance. This approach eliminates the need for a separate critic, making GRPO both efficient and robust. By fostering competition within groups, GRPO drives the model to consistently improve its reasoning capabilities. Uh, right. It's this innovation that powers DeepSeek's ability to achieve exponential results in reasoning tasks. Right. Understanding the GRP objective function. Let's look at the objective function, right? Like what is objective that the RL tries to, the RL model will try to improve, right? Yeah, right. That's it. The objective function in the objective function in GRPO defines how the model learns to improve its policy, driving its ability to generate high quality responses. Um, right. Let's see the GRPO objective function. Uh, right. So we have all that. I think like what is the E sign in mathematics? Let's say capital E, right? Not a small e. I don't think that's on once again. Right. So yeah, right. So we have 1 by G, okay, into when we'll minimize this. So the minimum of this, so which is we have pi theta, which is the new policy optimization, and the prob and we'll get the probability of a certain output given a query, and we will divide that by the old output, probability of the old output with the query, and we'll be multiplying that, I guess, with something called AI. We have no idea what that is. And also and yeah, we'll and between that and this, which is a clip function, I have no idea what that is, so we'll be going to that too. And we have an epsilon value. I think that must be at something, maybe at something like threshold, right? And then we're going to subtract that by beta into the KL diverge. Okay, yeah, I have no idea. The symbols are just maybe I've forgotten these symbols, but yeah, let's see what this is. Yeah, let's breaking down the components. Expected value. The expectation is over all input queries drawn from the training dataset P of Q. For each query, a group of responses OI G, okay, I equal to 1 to G is sampled from the old policy pi theta old. Right, got it. Um, the policy we have the policy ratio, which is the ratio between the probability of generating a response OI under the new policy theta pi theta versus the old policy pi theta old. This ratio indicates how the new policy differs from the old one for a given response. Okay, so we have a ratio, right? Hmm. So maybe say like it's like um hmm. So yeah, I think that is to improve the stability in training, right? To not have the new policy diverge a lot from the older one, right? So that like that is very common. Like we also we can see that in DPO also, right? In direct preference optimization, like within the loss function, this is incorporated, right, to increase the stability, right? Okay. This is like again, so to prevent the model to diverge a lot from its older policy, we have something like that, some ratio like that. Okay. And we have advantage estimation. The advantage of response OI, which reflects how much better or worse it is compared to others in a group. Right. So it is defined computed as RI, which is the reward assigned to a response OI, minus the mean. Okay, so we okay. So we'll get the reward. So we'll calculate AI, which is the advantage of a response OI compared to other responses. So we'll get the reward associated with, so for each response we'll be calculating this value. And so what we'll be doing is we will get the reward assigned to that specific response, and so we'll subtract that, and we'll see how much it differs from the mean reward that every like all that all the responses get, and we'll divide that by the standard deviation, I think, yeah, of all the rewards. Okay, So we have also have clipping. I think it's for stability. I think. Okay. Limits the policy ratio to a range. 1 minus epsilon to 1 plus epsilon to prevent. Okay. And we also KL divergence penalty. It regularizes the new policy by theta by penalizing its divergence from reference policy by ref. Ensures that the new policy doesn't deviate too much, maintaining consistency. Right. Right. Yeah. I mean, so what do we have here? Again, we have a minimum. Okay. So what does a clip function do? Clip function mathematics. Clip the values in array X to the range by replacing values less than. Okay. Okay. That. Okay. Yeah. So it limits the values between that range. So wait a minute. Where is that paper? This is that. So yeah, I think yeah, it clips the ratio bit. Okay, it clips the ratio bit of pi theta OIQ. Okay, between the range of 1 minus epsilon to 1 plus epsilon. So what we're doing is we are getting the minimum value of this. Okay, and we're multiplying that by okay, right. So in order to hmm, and okay, so the model has control over the reward functions. Mm, yeah, I mean, I mean we are getting at it. So what we're doing is we are getting the minimum value between the reward ratio, like the amount of divergence, and we'll multiply that by a relative. So what is that value? What is it called? What is AI called? Okay, the advantage of response, AI. So we are multiplying that by AI, right? Advantage of response, and and uh, we're making sure that this ratio does not. It stays in the ratio between. It stays in the range of 1 minus epsilon to 1 plus epsilon to prevent the model from. I think yeah, like to stabilize the model, right? I think that's what we're doing. And we're going to multiply that by the advantage of the model. So we get going to get the minimum value out of the both, right? So, hmm, like, yeah, like, I mean, it's the same thing, right? So we are just, what we're doing is we are getting the ratio and we're going to multiply that by by advantage, the relative advantage. And we're going to subtract the KL divergence to make sure that the model does not diverge too much from the reference line or from the reference policy, right? So that is that, right? So we got it, right? So that is the objective objective function, and maybe after getting through this section, we can understand this better. So yeah, let's see. So the GRPO objective function is like a recipe for teaching a model to get better at generating answer by comparing its own responses and improving step by step. Let's break it down into a easy to follow explanation. Okay. Imagine you're teaching a group of students to solve a math problem. Instead of just telling them who got the right answer or right or wrong answer, you compare all their answers to figure out who did the best and why. Then you help them learn by rewarding better approaches and improving weaker ones. This is exactly what GRPO does. Only it is AI models, not students. Start with the query. Pick a query Q from the training dataset P of Q. Let's say the query is what is the sum of 8 plus 5. Generate a group of responses. The model generate a group of GGG responses to the query. Um, Answer 13, 13, it's 12, it's sum is 13. Calculate reward from each response. What are rewards? Rewards guide the model's learning by quantifying the quality of responses. Types of rewards, accuracy rewards based on the correctness of rewards. Okay, so we have types of rewards. So we have our accuracy rewards, which are objectively determined. For example, solving a math problem, right? The solution to a math problem is straightforward, right? So it's like there's only one and only one answer. Okay. So we have format rewards. Okay. So we have a guideline, right? So we have the structural guideline, which is we want the model to also uh, have a thinking strategy and also include that thinking strategy in a uh, in a we also want the model to include the thinking strategy in some tags, for example think tags, uh, THINK, and also language consistency. Okay, so things such as language mixing, like different mixing different languages, or incoherent formatting, right? So based on that, we all can also assign the rewards. Okay, so what we are doing here is to have an objective reward, reward function that's more objective, and we don't have to like train a separate model like reward the model, right? We don't have to train another neural network to reward the model, right? So that is that. As a reward of RA to each response based on how good it is. For example, rewards could depend on. Okay, so we are not training a new model, right? So what we are doing, we're just having some objective checkpoints such as, does it include think tags, or is the formatting good, or is it accurate? We can just have a calculator determine on how accurate an answer is, or or if you are training the model for example coding tasks, so we can have some predefined test cases. So if the model performs in those predefined test cases, if the code does perform, then the high accuracy can be given to the response. So yeah, it's pretty straightforward. Mm. Is the response well structured in terms of format? Okay. Compare responses. So what we're doing is we are with AI, we are just comparing the responses. Uh, Maybe don't on that some numbers. In simple way, you can understand like this: the reward of answer minus average reward in the group by spread of rewards in the group. Responses better than the group's average get positive scores, while worse responses get negative scores. Right. So encourage competition within the group, driving the model to generate better responses. Okay. Update policy without clipping. With clipping, adjust the model pi theta to prevent responses with higher advantages, a greater than 0, while avoiding large destabilizing updates. If the ratio of the new policy to the old policy exceed the range of 1 minus epsilon to 1 plus epsilon, it's flip to prevent overcorrection. Right. So we want the model to improve slowly, uh, to include to make the to stabilize training. So we are clipping the policy updates between the range of 1 minus epsilon to 1 plus epsilon. Right. Makes sense. Example, if the new policy starts assigning too much probability to O1, clipping ensures it doesn't overemphasize this response. Right. So enable steady and reliable policy optimization even in complex tasks like reasoning. Penalize deviations with KL divergence. Hmm. To ensure the update policy doesn't deviate too far from the reference policy. If the model start generating wildly different formats, the KL divergence term discourages it. Okay. So yeah, we don't so we want consistency, right? So all these terms, I think, uh majorly, right, we are trying to improve consistency in training. uh okay, so we are generating group of responses, calculating what reward for each response based on predefined criteria. So we are not using another model. So I think so we are scripting SFT stage. So in the supervised fine tuning stage, we'll be having a model, we'll be having whole new training data, and we'll be uh, yeah, I mean we'll be having to train another model, which will like assign rewards to the output of the model, to each output, and we'll be training the model based on that. We'll be not having that, but we'll be having predefined criteria such as accuracy, which is objectively determined, right? For example, addition, subtractions, or predefined test cases, some predefined coding test cases, right? All that, and we'll be comparing responses within group to calculate the relative advantage. So we have a new term called AI, which is the reward of a specific um, output, minus the average response of the or average reward divided by the standard deviation, and update the policies, and also having stability with clipping, and we will regularize the updates to prevent the model from drifting too far from its baseline. Right. So why is ERPO effective? No critic needed. GRP avoids the need for a specific evaluator by relying on group comparisons, reducing computational costs. Got it. Clipping and regularization ensure the model improves steadily without wild fluctuations. Stable learning, right? Efficient training. By focusing on relative performance, GRPO is ideal for tasks like reasoning where absolute scoring is difficult, right? So we cannot absolutely determine a score, right? So yeah, I mean GRPO is ideal in such cases, according to, yeah, I mean it's ideal for in such cases. Uh, Real life energy. Hmm. Yeah, I think that's it. Yeah, so that is very good article. So let's take the key takeaways. I mean, I hope you two understood. I mean, if anyone is watching, I hope you two understood the objective function or equation, the objective equation that we are that the model will be trying to optimize. So yeah, so we'll be sampling from the old model probabilities for each output, uh, each output sample from a query from the old model. And so what we're doing, we'll be getting the ratio between pi theta. Uh, so the probability that the new policy will be giving to each output divided by pi theta old. So this ratio so as this ratio reaches one, it means like it means that the model is not changing so much, right? Okay, got it. Um, hmm, right. So got it. So and then so this ratio, right? We do not want the ratio to be too high, right? Okay. So we'll be multiplying this ratio with uh uh in with a new variable metric called advantage, which is basically the difference between the reward for each. So the advantage of each response is given by the difference between the reward of that response by the mean reward for a group divided by standard deviation. So and so in order to improve stability, we'll be having a clip function, which we will which will clip the ratio between the range of 1 minus epsilon to 1 plus epsilon, right? Okay. Hmm. So got it. And we're multiplying that too by AI. Got it. And so we'll be getting the minimal value between this. Okay, right. Hmm. Right. So that's okay. And then we'll be also having KL divergence term, right? So it's like if you want to improve the reward function, you have to reduce scale divergence from the basic reference line to not to stop the model from going crazy in the training phase. Okay, got it. So that's that. Right. I mean, yeah. And okay, and we also have the formula for KL divergence, which is pi reference of OI by Q by pi theta of OI given Q minus log of pi reference of OI by Q by pi theta of OI by Q minus 1. Um, right? Hmm. Okay, so we have E alpha, epsilon and beta are hyperparameters, right? So we can set them to like arbitrarily by our choice for our specific case, right? And AI is the advantage. Okay, we have that. A common producer assistant. Okay. The user asks a question and the assistant solves it. The assistant first thinks about the reasoning process in the mind and then provides the answer. Hmm. The reward is a source of the training signal, which is decides the optimized reward training template. I think that is enough for the today's video. I think we have stayed long enough. We have got a good introduction to DeepSeek, Arun. There's still a lot to learn, and maybe to use these models, right? So I think that is enough for this video. Thank you for watching if you did, and I'll see you in the next video. Thank you for watching.